IIT Kharagpur on advances in instrumentation for machinery condition monitoring. So I'd like to take the opportunity to introduce Professor Mohanty, who has more than 30 years of research experience in the area of machinery condition monitoring and acoustics. And his research is both in fundamental and applied levels, and is vital in providing immediate solutions to engineering problems. Some of the current research activities are in the areas of acoustics, are in the development of new natural acoustic materials, acoustical metamaterials, holography, microperforates, etc. And the research is also in the areas of machinery fault diagnosis, are in the areas of fault prognosis, incipient fault detection, instantaneous angular speed estimation, and model-based fault detection, remote sensing, wireless data acquisition, and motor current signature analysis, etc. So I welcome you, sir, and I'll hand over the system over to you for your presentation. Thank you very much, sir. Over to you, sir.
Thank you, Jamil. Thank you. Yeah, okay. Are you able to see my screen?
Yes, it's in the process of coming. Right now, it is blank.
Okay.
Just I think it may take a few seconds.
Able to see it?
Till now, it is.
Able to see it now?
Not yet, sir. We are waiting.
Okay. Can happen in the morning also.
It's a dark screen. Although there is some changes, like it is changing, but still it is.
Sir, it is an internet issue at your end.
Internet?
Yes, sir, is having some internet issue, but I think
I'm using.
it's from the phone itself, I think. So maybe you can reshare it again, and maybe you can keep.
Okay.
Yes, sir. Now it is, I think, visible.
But it is taking some time to come up. That means.
Yes, sir. It's visible now. Your screen is visible.
Okay. Okay. I cannot see myself though. But anyway. Fine.
Okay. So you may proceed, sir.
Yeah. Thank you, Jamil, for inviting me. Before I continue my discussion this afternoon, if there are any questions from the first half, this morning's presentation, is there anybody with any questions? Or you can write in the chat box. There are. Okay. So what I will do is, I will go back to where we left.
So there is one question Bhavik Patel, he has asked, please explain again aliasing topics.
Okay. Well, no. Okay. Let
Perhaps
me
I think
see.
we can do it afterwards once this thing is over.
Yeah. If you can please keep it, we will do it afterwards. Okay.
Sure.
Because I need to bring out the.
Sure. Sir.
Okay. Anyway, coming back to this discussion on advanced instrumentation technique. This morning, I told you about one of the emerging areas is this motor current signature analysis. First, let me tell you why this is so powerful. See, if you go to any industry or any plant for that matter, if you will come across many different mechanical driven units. For example, it could be a fan, it could be a gearbox, it could be a blower, it could be a crusher. The prime mover in 90% of the cases of machines in the world are actually electrical motors. So electrical motors form an important part of the machine. Imagine you have a pump, a very excellent pump, but this pump is being powered by a motor. So if the motor has gone bad, the pump is of no use. That's number one. Another area where this motor current signature analysis helps is for the fact that, see, a motor can be in some remote location. The motor is drawing power through a conductor, electrical wire. So electrical wire can be laid from your control room to the location where the motor is placed. So we can easily measure the motor current, not the absolute amplitude of the motor current, but actually we can record the current waveform. You all will recall, right from your basic first year electrical engineering and an RLC circuit. If I have resistance, inductance, and capacitance, and I give, they are in series, and I give a voltage V0 sine omega t, I will have a current drawn I0 sine omega t plus phi, some phase difference. The current drawn will be also a sinusoidal waveform with a phase difference that depends on the values of the inductance and capacitance of this circuit. Now, this current waveform actually carries lot of information. This morning I was telling you regarding the case of the Oak Ridge National Laboratories in US, where in 1974, this is what has been reported, they were monitoring the opening and closing of valves in a nuclear reactor which were being operated by servo motors. Just by monitoring the current waveform, they could for sure say whether the valve was closed or valve was open. So these are the first cited application of motor current. And somehow after that, this was not encouraged. I would not say encouraged. People in the condition monitoring domain were more focused on vibration monitoring. Then in the mid 90s, there were few researchers out of UK who did a motor current signature analysis for finding out faults in electrical motor. But there's a small story. I do not know if I have put that story here. Yeah, what happened? We had a project from the Ministry of Information Technology then, that in CNC machines, let us find out ways to monitor the tool wear. In those days, in mid 90s or 98s. Okay. Yeah, thank you. So in those days, there was no such method of directly monitoring the tool wear, because the vision systems which are apparently available now, the IR based, infrared based temperature sensing methods which are available now were not there. So we thought, by we mean me and my team in IIT Kharagpur, we thought, why not we instrument we had a vertical milling machine which was doing some cutting operations. Why not we monitor the different parameters of the machine when it is machining a certain workpiece? So we instrumented it with force transducer, cutting force dynamometer. We put vibration, we measured acoustic emission, and incidentally, I also put a current measuring sensor, which is actually a Hall effect current sensor in the spindle motor current conductor. And the first time when we ran the milling machine with no load, it was just spindle was running at a certain RPM, I could see a sinusoidal wave of the current corresponding to the rotational frequency. By rotational frequency, I mean the rotational speed of the spindle motor. But when we started to machine aluminum, dry aluminum, we milled the face milling on the aluminum block, I saw the current getting modulated. By modulation, I mean there was increase and decrease of the amplitude of the current, which normally I thought it to be a sine wave. Okay, I am a mechanical engineer. Okay, and I really did not dig into the motor current much then. I thought, in my first year, we have studied RLC circuits, so it will be sinusoidal. But once I noticed, it was actually, to be very honest, it was just a discovery with me and my students that the current is getting modulated. But then what we did, we changed the workpiece from aluminum to steel, where the forces are higher, cutting forces are higher. I saw the current modulation index increased. That means there was a lot of increase and decrease of the current. And then we did the FFT, or fast Fourier transform, of the captured current time waveform. And then we saw, in fact, these videos are not here today. I mean, these slides, these are there in my NPTEL videos. You will see in the iitnows.com. Okay, but I will tell you today I'm going to present, this is the history, okay, how it came to us, and then what we did. And then I will tell you what is the current state of the art. And for that, I have the slides. So this is the history. And because this is about more than 20 years ago, this is now there in my textbook also on machinery condition monitoring principles and practices. But anyway, coming back to the story, when I see modulations, I saw side bands around the supply frequency of the motor. Because this motor was driven by a variable frequency drive, I could see side bands. And when the load increased, when did the load increase? When I cut steel, because steel is a stronger material than aluminum, so more cutting forces were required. I saw the increase in the height of the side bands around the supply frequency. So this was my discovery. Then I thought that means the load on the motor is influencing the motor current being drawn by the electrical motor. I took it a little further. What if this load is because of a fault in the machinery? Fault in the sense there's a fault in the gearbox, fault in the bearing, fault in the pump. Let me tell you, this is a very, very important technique. Today, we are talking about electric vehicles. Okay. There are major German OEMs, you must have heard with electric vehicles, people are talking about batteries, battery life, battery density, battery disposal, battery contact resistances, and how quickly they can be charged. But everybody is, I would not say silent, at least in the public domain, nobody is talking about that electric motor which is driving your electric vehicle. People are talking about BLDC motors, but there are motors, even in cars like BMW, i3, i8, they are no longer BLDC motors, they are PMSM motors, okay, permanent magnet, synchronous machines, where the rotor is a heavy permanent magnet, okay, but the stator has coil windings. So imagine if you are, so what is the, I'm just again, like I pose questions so that you can dream. Today we are talking about auto rickshaws with BLDC motors. We are talking about scooters with BLDC motors. We are talking with high-end cars like Tesla, i3s, etc., with PMSM motors. What if the motor has gone bad? You are stranded on the highway, you have the fullest charge in your battery, still the car will not move. So this is the recent phenomena. But coming back to my in 1998, okay, when we first found this in this CNC milling machine, I immediately looked into the literature and I found that there was no patent as to finding out faults in rotating mechanical devices using a electrical motor. So I filed a patent. Patent has been awarded, and you'll be glad to know I have licensed this patent to many companies in the country, transfer technology to companies in the USA, wherein any device, be it a pump, be it a crusher, be it a rolling mill, if there is a fault in it, I just I can monitor through the motor current. And the physics is very simple. I'll show you in the next few slides. The physics, it is very, very simple. There's no rocket science here, but then now its application is enormous. So the idea is, first is I need to measure the current. I can have current transformers, I can have Hall effect sensors, and I can have a Rogowski's coil. These are all measurement devices to measure current. And then once I have the current, I can have, these are very cheap data acquisition units, less than 15,000 rupees, USB plug and play. You put it in an FFT analyzer, or you have on a microcomputer. This is what we started with in 1998. So all I require is an Hall effect sensor, data acquisition unit, and an FFT analyzer. Look at the current spectrum, monitor the sidebands. Okay, and then we can find out faults in the electrical motor, faults in the mechanical unit being driven by that electrical motor. Okay, let me now go to the theory. Why these sidebands occur? These are very simple mathematical equations. See, for example, in a motor, there are actually two components of the current. One is the magnetizing component in the stator, and one is the torque producing current, which rotates the rotor. Okay. And then if you look at this, R, Y, B are the three phases, and the resultant is this ISM, the torque producing current, and the magnetizing current. Now imagine the torque which is applied as a load onto the motor. This load could be because of a defect, because of an operation. So it has a mean component T naught, T1 at frequency F1, T2 at frequency F2, T3 at frequency F3. So I have taken arbitrarily 3 frequencies at which a fault occurs. Okay, these could be related to the mechanical fault in the system. So if I add them up, the magnetizing component is this, and the torque producing component are the cosine functions, which are 90-degree phase apart from the magnetizing current, so ISM and IST. So just in one phase, just an R phase, I add the magnetizing and the torque producing current. If I add them, trigonometric addition, I will land up with the final expression where there will be a constant current, some amplitude I naught, at the supply frequency where Fe is the supply frequency to the motor, and then certain amplitudes of the side bands. But this is very important. Fe minus F1, that is supply frequency, side bands around supply frequency at a spacing of F1 plus minus F1 plus F1 minus F1 plus F2 minus F2 plus F3 minus F3. That means as many fault frequencies are there, I will get that many side bands around the supply frequency. Side bands of components of torsional vibration across supply line frequency. This is what the theory says, and me and my student, we figured it out. And this is pure physics. There is nothing, or electrical engineering. There's no rocket science or machine learning here per se. So then we came up with this algorithm. We started this work somewhere in 98. By the time we published it, it was in 2004 in Mechanical Systems and Signal Processing. This is a highly cited paper in the world. So we now you see any frequency Fi, I is equal to 1 to n. Fi's are these are the fault frequencies. Okay. Let me see if my internet is still down. Connected. Okay. Anyway. So what we did in the laboratory, because this was a theory, I observed this in my CNC machine. We wanted to do it in the laboratory. This morning I was showing you the same setup. We use the same setup. Herein, we have put Hall effect sensors to measure the three phases currents being drawn by the induction motor. I have a gearbox loading in it for the generator output, and we monitored the vibration signal. We found out the second gear, because this was being operated in the second gear, input shaft, etc. Again, in the current signal, we could see all these things: left hand and right hand side bands of second GMF across line frequency. So that means the motor current signature analysis was established then, that this is non-intrusive. It is possible to detect and diagnose the fault as early as possible. The current gets modulated, so we developed algorithms to demodulate the signal and find out the defect frequency. So now you see the power of this technique. I started with an example of a nuclear reactor. Imagine submersible pumps, which are 30 meters, 100 meters down in the ground. No matter whatever, you may be a vibration expert, if you do not have access to the submersible pump underground, okay, to measure its vibration. You may have permanently installed some accelerometers, but in situ, we just cannot go on the fly and install accelerometers. Oil rigs, drilling bits. These are all nice candidates for MCSA. And again, on the ground, MCSA can be used because there is current carrying conductor going from your control room to the motor which is driving the whatever be it fans, blowers. Now, again, let me tell you, today the technology is such. We just had a discussion on wireless data acquisition. Imagine if I have an Hall effect sensor or a current transformer with an Wi-Fi transmitter. Today, there is a foundry in Hyderabad where they are monitoring all their operations, not through vibration, just by remotely measuring the current at all locations. Health of an EOT, electric overhead traction crane on a factory floor, rolling mills, steel plants, cement plants. They are very critical motors. And everybody need not go to the machines. Paper mills, so many motors are there. Press rolls. All those motors can be monitored. So I want to draw two techniques here. One is using motor current signature analysis to find out faults in electrical motors per se. Other is using motor current signature analysis to find faults in the mechanical unit being driven by a electrical motor. You are talking about electric cars, EV electrical vehicles. The PMS motors drive massive gearboxes. What if there is a problem in the gearbox? And believe you, the technology is such, the local garages neither have the technology nor the equipment to maintain or fix such electric vehicles if we are stuck on the highways. So now MCSA along with Wi-Fi puts all the algorithm in the cloud. You could be monitoring the vehicle. You could be taking diagnostic measures. You could, if so for example, just to go to the next station, you may reduce power and creep down to the next station. So many things are possible so that you can home the machine to its home position. Okay, robotics, another very important application where MCSA using, along with the encoders, where we could use the positioning through the monitoring the faults through the encoder, instantaneous angular speed. So many things, especially because you all are academicians and students and researchers, I thought, these are areas where people can grow. Okay, and this is happening. Again, another example is this submersible pump which I was talking about. Submersible pump, because of the slurries and the debris, the amount of failure is pretty severe because of corrosion damage, wear. So we in the laboratory again fabricated impellers wherein we could remove certain vanes, and then we could create artificial defects of the submersible pump. And then in the laboratory, of course, we use the submersible pump in our water tank. Okay, so AC supply, UPS, speed controller, pump, all effects, and did an analysis. And this is a current transformer. Measure the current spectrum. We could come up to the at 40 Hertz supply frequency. Normal impeller, broken impeller, there is a difference. Okay, and if computer algorithms are there to notice this difference in the severity of the amplitude, it is observed that the severity of the defect increases, heights of sideband increases. So from -62 to -58. So if your measurements are good and your resolution is fine enough, you can detect faults in machines through motor current signature analysis. Okay, this was another experiment which we did. The monitoring of health of a gas turbine using the motor current, because the gas turbines in this Navy, this was in INS Slurry actually, they have a test gas turbine generator set. If you talk about in our frigates, there are 2-3 such gas turbines, okay, and they drive the generators which are used generate power, and these generators are sometimes used to drive the propulsion systems, okay, to give enough current. So by monitoring the generator output, the ripples in the generator voltage, I can find out for the characteristic fault frequency of the gas turbine. We also did this through vibration monitoring. Okay, this was about 2 decades ago which we did. So as you will tell you get an idea. This motor current signature analysis, is immediately being used in the industry. I mean, this slide I had thought 2 decades ago, and today let me tell you, any technology which comes out of a research, it actually takes a decade to come to the market. Today, the technology is such that if you open up internet, you will find out companies with a suitcase, they will have a clamp on current emitters and an analyzer telling you faults in electrical motors. But the physics is very simple, and this we in the world, I could say, were one of the groups very strongly we encouraged its propagation rather, up to a level where we the technology to us, and it's a very simple technology: submersible pumps, reactor coolant pumps, reduction gearbox in gas turbines, power plants, electric vehicle drives, windmills, cement plants. Every time people are using submersible pumps, analysis. Okay, and this is the patent which I was talking about. An electromagnetic device-based system for fault detection and identification in rotating mechanical components. Okay, so this came out of our peer research, and we got the patent, and now we have licenses to many industries. Okay, I will switch gears now and come to another technique. Again, this morning I had told you something regarding thermography. Okay, and I will go a little further. It is just not thermal imaging, but many things can be also found out from thermography. Particularly, mind the words, please note the words, rate of temperature rise. That is very, very important. So what we did, this is a setup which we have in the laboratory. We have a motor coupling driving a shaft supported on bearings. We measured the current, we measured the thermal imaging with an FILR E60 camera. We looked at the analysis, we measured the vibration. Okay. This is the setup. This is a thermal imaging camera put on a tripod. This is the rotor, and these are all laser, and this is a thermal imaging camera. We are trying to focus on the bearings, get heated up. Okay. So what we did, in this rig, we tried to put different couplings between the motor and the shaft. These are 3 different: rigid coupling, helical coupling, gear coupling, etc. And we artificially created misalignment between the shaft and the motor shaft here. Okay, shaft carrying the bearings, the bearing loader, and the motor shaft. And we monitored the temperature. Okay, at the NDE bearing. Okay, sorry, go back. So what happens? We measured at different RPMs. The rotor was stopped, and again the temperature fell down because of Newton's law of cooling. Okay, this was what was observed in a standard room. Now, what we did, these are all the infrared images. Okay. But at steady state, more or less, they will all come to an equilibrium temperature. So thermography will only tell you all have reached a certain temperature, which is understood. But the point to be noted is, if a component is misaligned, which all of you must have sensed in your daily life also, the rate of temperature rise is very sharp if it is misaligned. Okay. So I'll come to, so if you look here, this is the normal shaft. Normal shaft will have a temperature rise. But if it is misaligned, look at the slope between these two dots, two black dots. Misaligned, the rate of temperature rise is very, very high. And this can very easily be captured by a thermal imaging camera, where we are collecting data, maybe 30 frames per second or even 60 frames per second. These videos were being collected, and then we plotted the temperature curve. So what I mean to say, permanently we can embed certain temperature samples, sample them at 30 or 60 frames per second, and monitor the temperature. Okay, and this is important because these are all rotating. So I possibly cannot put a temperature on the rotating device, thermocouple on a rotating device because of the cables. But if I have an infrared camera focused and shooting at that surface, I can record the temperature. Yeah, this was being logged at 30 frames per second. We had to set the emissivity, and then with this software we could capture the images. Okay. And of course, we also measure the vibration with normal misaligned. That is true. But what I meant to say is, again, these are all very cheap techniques of monitoring defects where places are inaccessible through temperature monitoring. Okay. So rate of temperature rise of coupling compared to bearing can be used as an indicator for incipient misalignment detection in shafts. The rise time should be measured within the time constant of the system so as not to capture the steady state temperature of the bearing housing. Okay, it has to be quick enough, because if it has reached steady state, there's no point. It has to be a faster response. And this can be used in location where it is cumbersome or difficult to instrument or access. Okay. Now, having talked about vibration, torsional vibration, and then thermal imaging, motor current, I will now talk about some of the computational tools being made available today in terms of analysis power, because end of the day we are interested in fault prognosis. Okay. So the ISO 13374 standard, which says the most important part is the sensors, data acquisition, which we did. Data has to be put, detect its state, know its health. These are the fault diagnostics. And then, of course, with lot of algorithms, be it machine learning or be it model-based, I have to do a prognostic assessment and then generate an advisory to the management. So this is, when you say that in a plant I am doing condition monitoring, your management would be interested to implement the functional blocks of ISO 13374 in your plant, so that there are dedicated teams doing data acquisition, database management, analysts doing the state detection or fault detection or health assessment, again doing a lot of data analytics and cloud computing to find out the RUL, and then generate advice. Some places you may, by advisory generation, I mean some places you may recommend total replacement of a certain component. Some place you may replace, you may say an overall OEM or a maintenance for a particular component, and so on and so forth. And today the technology is such, just by doing fault detection, nobody is happy. We have gone a little further. What is the end life of my asset? And when I say asset, it is not machines people are talking about. And again, now people are talking about digital twins. People are talking about physical system is fine. Can we have a mathematical model digital twins wherein we give in different scenarios of input and see what are the failure modes, what are the prognostic modes. Okay. And this is very, very important. Okay. And today, if you go to the modern control room, you see nobody is there. Okay, why? Because all those instruments, they are being recorded, data log. And if the personnel come their lunch break, actually they are gone on lunch break, but nobody is there. Okay, but then if you had been to a steel plant or a power plant, or maybe even today, there will be people, of course, no longer they write. They used to write in logbooks. This is the temperature, this is the flow rate of this sensor, that sensor. Gone are those days. Today, there are trip alarms and automatic data trending, logging, and alarm levels are there. They will warn you if there is an impending problem. In fact, the technology is so robust, they will tell you what needs replacement, what needs care, okay, what needs more critical observation. These are all very standard procedures nowadays. But the physics is the same. And see, basic vibration, basic electrical engineering, thermal imaging, oil, wear debris analysis, they remain the same. But again, as I was telling you, because of the advancement in electronics, miniaturization of sensors, high computing power, Wi-Fi and internet, we have reached this level which is there. Mechanical engineering, I say yes, as long as it is mankind, there will be mechanical, yes. Mechanical engineers also must know the basics of signal, digital signal processing should become a core in every engineering curriculum. Every engineer today must know digital signal processing, FFT, data acquisition, rudimentary signal analysis. Okay, it is so powerful. So the elements in the CBM cycle, okay, all of the network. Are you able to see me or hear me? I hope there is no problem with the network.
Yes, sir. Please continue. We are able to
Hello. Okay. Okay. Because I just saw a sign that the internet is unstable. So again, you see, I have told you about sensors. Talked about accelerometers, velocity probe, eddy current probe, Hall effect sensors, current transformers, etc. What if this sensor has a problem? So today the technology is such, this sensor will tell you if there is an open circuit. Sensor will warn you. And sensors, which are known as threads-based sensors, they have an electronic chip embedded in them where its sensitivity and its identity is there. So as soon as connect to an analyzer, you do not have to set up the sensitivity of that sensor. It is automatically read by the analyzer. And you will be measuring in the mechanical unit the sensor was designed to measure. So smart fault tolerant sensor is very, very important. I am not saying that, but cables is a problem. I'll just give you an example. We are this motor current analysis. This Qatar, they are hosting the World Cup. Aren't they this time? Football World Cup. Okay. So the Qatar government has appreciated motor current signature analysis. So, they have, we have a consortium now, myself from IIT Kharagpur, Texas A&M University in Qatar, and the Shell Corporation. It's close to $500,000 US project, wherein we are using MCSA, motor current signature analysis, to find out the fault prognosis in power generation, power distribution. Okay. When you talk about power generation, we are talking about generators, motors, transformers, power distribution, switch gears. But interestingly, we are also, of course, not me as a, not our team at Kharagpur, we are looking more into motors and generators. But a team in, my partner team in Qatar, they are looking into the cable faults. When a cable is buried under the ground, an electrical cable, what is its life? Everything is good, but your electrical cable, your plant has a problem. Plant is not good. Have you ever realized that? Transformer having problem, transformer outbursts. Okay, so these are issues we should look in totality. I have seen my students or my colleagues buying imported costly sensors. They would have forgotten to buy the right cable because the cable was expensive, as expensive as the sensor, and the market buy a very cheap cable and they get spurious signals because of the, again, the frequency response of the cable, the capacitance of the cable does play a role in limiting the frequency content of the signal which is conveyed through the cable. So as engineers, we have to keep everything in mind. So that is what I meant. This is very, very important. Best sensor till the end, when the current and the cables play a very, very, very big role. Of course. Next is, of course, the data has to be collected. I did not spend much time on the data aggregation aspect. If there are questions, we will discuss that later on. But data has to be, certain pre-processing has to be done because data could be having certain spurious noise signals. So this has to be filtered, features has to be extracted, and then fault classification. Nowadays, a lot of machine learning algorithms are there for fault classification. We have to then predict how the fault evolves, either through a certain physical model, or through experimental observations, or through machine learning, and then recommend what I told as advisories, schedule a maintenance or recommend a repair or replacement. So the fault diagnostics techniques are model-based or data-driven signal-based. The data-driven signal-based is very, very simple. I just gave you an example wherein the amplitudes of the sidebands would increase. Amplitudes at a particular frequency would increase. Model-based, certain model tells you that the model has to be, you make a physical model, mx double dot plus cx dot plus kx is equal to some forcing function. The estimation of m, c, and k for a model, when I say m, c, k, it will be a matrix of m, c, and k. The model can be robust by putting in the experimental observations, and then we can minimize the error between the model and the experimental, so that once your model perfectly predicts the experimental observations, I can now do an inverse problem that this is my response x or x dot or x double dot. What is my force? So these kind of model-based techniques are available for systems where the system can be modeled in a mass spring dashboard systems. People have taken advantage of the finite methods to make a model. People have used lump parameter models for developing models, and people have used Kalman filtering based models to minimize the error, make a better estimation, etc. Okay, these techniques are there. Okay, and then another thing in the data driven, earlier, we used to have a fault classification, or you can have a fault pattern library. You can do a comparison, or we can have a feature vectors, and then we can make a decision and fault classification, etc. Okay. And then, of course, we can diagnose the. So data diagnostic methods, we can have certain alarms, both above and below the method level, statistical correlation, fuzzy logic, neural network. A lot of neural network based methods are there. Physical method, the famous Paris equation, where the crack propagation model can be used, or finite element based model can be used. So today in the morning, in the welcome ceremony of the inaugural session, your dean was mentioning about this main principles in Industry 4, or what is happening. We cannot neglect Industry 4. So Industry 4 is basically, I know Dr. Bhujangaraj is Industry 4 in this week. So we are using, it is interoperability. This is communication between equipment operators through sensors. Virtual industry, digital twins, we can do maintenance, and we can have decentralized decisions. Okay, these are all possible in Industry 4. So in the machine learning techniques, these are all available. Supervised methods. I will not go into detail. This itself is a course, okay? And nowadays there are a lot of popular courses in Coursera in machine learning, artificial Coursera courses from Stanford University, MIT, Cambridge. I mean, those of you who are interested must learn one of those techniques. There's no rocket science. It is a good amount of algebra and probability and a very rational flow. Okay, but again, as mechanical engineer, I must caution you. Please, in the name of machine learning, please do not ignore the basic physics or the electrical engineering basics. Machine learning is not going to change the output of Ohm's law or Newton's law, okay, or Faraday's law of induction. Machine learning cannot change it. These are theory based on a certain physics. Machine learning only helps us crunch a lot of data into some meaningful observations, which humanly or the brain can do it. But because the volume is so large, we possibly cannot track so many variables. Okay, very simple thing. And again, I always tell, computer is the greatest fool. Okay. So computers will only do whatever it is told to them to do. Now in machine learning, computers develop algorithms based on the data they have been supplied to. Okay, so computers cannot generate data on their own. Okay? They may develop certain algorithms to help crunch the data based on earlier data. So keep that in mind. And machine learning is not the end. Okay, it is a technique. Like 40 years ago, when finite element came up, people thought, we could model everything by finite element. Then came boundary element. Okay, still we can do a lot of things with finite element. Similarly, it will become, it is a tool. Machine learning is a tool. So we give them data, we get some output. Okay. So having said this, the future of condition monitoring will be availability of smart and fault tolerant sensors. I just give you an example. If a sensor is faulty, what could go wrong? Laser-based monitoring, saw in the morning the examples. Embedded systems for IoTs, very small FPGA systems. Wireless remote monitoring. Motor current signature analysis, you saw the power of it. Machine learning and data analytics is a part of it. And of course, online monitoring, model-based, and the last one is very important for prognosis. We have to live with them. Okay. With this, I will take a 10-minute break. If the organizers are okay, can I take a 10-minute break?
Sure, sir. I
Are
think
they all-
it's okay to have a break, and we will return after 10 minutes. I think it's okay. No problem, sir. Sir, yes, please, sir.
Sure. Thank you. Yeah, as I was telling you, so far between this morning and right now, we have looked into certain past issues in measurements, sensors, certain analysis, and of course now the recent trend, if I was to let you know, is miniaturized sensor, lightweight, wireless, motor current being another technique which is coming up. And of course, the help of machine learning, data analytics. And finally, it is no longer condition monitoring, but rather fault prognostics or remaining useful life prediction. That is what is the future. And everybody in the industry is not looking just to go to a machine and know its fault. They want a complete solution. Okay. And that is what is being done by many of the fleet owners. Many large manufacturing plants are looking to an overall condition of their plant. They want a dashboard wherein they know precisely which component needs failure, which component requires replacement altogether. So this is what we will tell. Now, just to lighten the mood, I thought I will show you pictorially some of the facilities, etc., which is there at IIT Kharagpur in the our machinery acoustics and condition monitoring laboratory, and tell you small stories. Then I will come back to the future of using IoT with MCSA, and that is what I will end before I take up, and then after that I will take up the questions and we'll have a question and answer session. Okay, as I was telling, on-site vibration monitoring, even in submarines, the problem with in the submarine, the major problem is actually vibration isolation, because there is a space hardly anybody can walk through. There's a lot of pumps, and vibration isolation is a very, very big issue in submersible in submarines. This is in a submarine which I was there in Bombay. Okay, they were showing me the sonar measurement systems. And this is at Medak, Ordnance Factory Medak, where this BMP, they want to, the earlier BMPs did not have any facilities for onboard monitoring or the no longer diagnostics, even onboard to know what are the parameters. So we have taken up a project with them. Of course, nowadays, the new BMPs come up with already instrumented systems wherein you can know the ride quality handling. When I talk about ride quality handling, of course, when we buy our cars, etc., they have the best ride quality handling. And of course, the manufacturers compare between different models. A ride quality in a BMW is like a sports car compared to a ride quality in a Mercedes, for example. Both of them are the same quality. And then coming to this armored vehicle or even dump trucks in the mine, if you go to an open cast mine, and by the way, India has a largest open cast mine in Gewra, okay, that is near Bilaspur in central India. Day in, then day out, the mine drivers, about 8 to 10 hours, they will go along a haul road, go to the shovel area where the overburden or the coal mine will be scooped, put in the dump trucks, and then they will be driven back to the point where they are downloaded for onward transmission. The steering wheel vibration, the ride quality, these are factors which affect the driver's performance. Having said that, we are doing a project wherein again remotely we are monitoring 2 dump trucks in a mine in Sonpuri Bazari in eastern coalfields, where we have instrumented them with vibration accelerometers. We have miniature data acquisition unit with a cloud interface, and data goes to cloud. We can see it at Kharagpur. Our partners in Sweden, our partners in Dhanbad, in Ranchi can see the data, and my students can also access the data. Okay, and this is almost every day we get about 10 minutes of data from the dump truck. Okay, I was mentioning about this railway locomotive. Okay, this was a locomotive wherein we did a lot of noise control. But while we are doing this noise control, I figured out in this locomotives today also they have a diagnostic module. You may call it similar to a black box in an aircraft, wherein all the engine parameters get logged in, and after a certain interval, the driver can, or the maintenance crew can retrieve those data and know the condition of the engine. This is a standard practice in Indian Railways, by the way. And this is again, we are doing speed trials in the same locomotive. I just wanted to give you a feel of the instrumentation used in doing such on-site measurements. So this is the yellow Pelican suitcases. This is my favorite 8-channel tape recorder. These are the signal conditioning amplifiers for the accelerometers. We are measuring the panel vibration, and we have also put some microphones measuring the noise and vibration when a locomotive was being driven from Kharagpur about 30 kilometers to another station called Narayangarh. We are seeing the ride quality of a locomotive. Okay. These are some of the facilities which we have in our condition monitoring. Almost all the noise and vibration measurement equipment, all sorts of analyzers, lasers, and of course now we have added a lot of setups for measurement. So I'll give you a pictorial view. This is the view of the laboratory. In fact, right now I'm sitting in one of these chairs here. Okay, this is the lab. You can see the Omni sound source, the exciter. Okay, and there's a panel behind me, and this is the machinery fault simulator. I'm sure many of the universities must be having that. I'm sure Aligarh Muslim University in their labs must be having one of such fault simulators, wherein we can simulate bearing faults, rotor faults, gearbox faults, pulley faults, motor faults, alignment issues. There is also pump setup. So these machinery fault simulator is an, I may say, is an industry standard for teaching machinery fault diagnosis to students. And almost every university throughout the world has one of these kits. And we have used this kit to do many controlled experiments to validate our algorithms, because whatever algorithm we make, it has to be validated. And for validated, we need validation. We need a lot of controlled experiments in real nice conditions. And you can see we are putting this accelerometers on the bearing mounts, on the motors, on the gearbox. Another thing which I must tell you is many times in condition monitoring, many problems happen because of resonance. So sometimes in situ, we may have to find out the natural frequency of a machinery or a machinery component. This is a imported portable air conditioner which we are doing the model testing. If you can see the laser here, this has been suspended from the ceiling to give you a simple supported boundary conditions, and this is an exciter, and the same exciter we are using to find out the natural frequency of a refrigerator. This is an impedance head wherein you can measure both the force and the acceleration at the same point. So I can find out the driving point impedance. Okay, and here at the far end you can see a human torso, which is used to measure the sound using a binaural setup. This is the amplifier for the exciter. This is an amplifier for the hydrophone. We also have an underwater tank. This is an IC engine test rig wherein we have used that optical encoder to find out faults in that IC engine. We also do a lot of sound quality measurements on that. There are a lot of signal analyzers, and there's an 8-channel Horus signal analyzer, there's a pulse signal analyzer. Okay, a lot of industrial vibration meters. Okay, this is a measuring amplifier which can take a charge type accelerometer or a deltatron accelerometer. A deltatron accelerometer is actually an accelerometer where the charge to voltage amplifier is actually inside the accelerometer. So they are given this name deltatron. Deltatron is by this company B&K. There is a company, Pizzotron, Isotron, IEP. These are all trademarks of different companies. Okay, all they require is a 2 to 4 milliampere power supply, and they will give you a voltage output. Okay, this is an industrial accelerometer, very robust, harsh environment, and then we have an handheld vibration meter. Yeah, this is the view of the rotational laser vibrometer, and which costs about 30 lakhs. Okay, this is the signal conditioner. It of course has a laptop also, wherein we can do the post processing. This is a single point laser vibrometer, okay, measuring the vibration, okay, non-contact of the bearing. This is a digital data recorder, okay, Yokogawa 8-channel. So you see all these flags behind me. These are the countries I have visited, so I try to collect the flags of the country which I visit. We have a lot of signal processing equipment. For example, this is an amplifier for the exciters. This is the amplifier for the rotational laser vibrometer. This is a filter set where we can have a set of low pass, high pass filter. This is again another amplifier. This is an oscilloscope. This is a wave generator, multimeter, digital power supply. This is an 100G electromagnetic shaker, okay, which we can, this is a tune mass damper system which has been put. Yeah, I have this book, Machinery Condition Monitoring of CRC Press, published in 2014. This is quite popular throughout the world, and people use it. Of course, it is due for a second revision. I am not getting time to work on it, but I have to do it pretty soon. Of course, coming back to education, of course, and it is good that the organizers. Am I muted? No, I saw. See this. Coming back to higher education, see a lot of these courses like this do help you get an exposure. But let me tell you, there is no course like a dedicated 40-hour lecture in any university or institute. In our master's program, we have the PG courses. Of course, now all these offline courses have gone for a toss. And fortunately, my NPTEL lectures have come to a help at this time, but nothing like interaction in the class where the teacher interacts with the students and then you get to go to the labs, etc. I hope after this outbreak subsides, we can come back to our offline classes and we will go back to our normal courses. And we, of course, in IIT, we hold a lot of continuing education program, but now my colleague like Dr. Sidra is organizing. So I eagerly jumped in when she mentioned that she's going to organize this course. I told her, well, that's good. She's taken a lot of pains to organize this course, and I thought I would jump in to help and deliver a few lectures. But at the same time, we may not be doing justice in a couple of hours of lectures. It is only a teaser. Okay, and to those of you who all are attending this, there's a lot to learn, and every day the technology is changing so fast. I have been doing this for last 25 years, but let me tell you, every day I'm learning something new. Okay, and that is what keeps us running. Of course, at the same time, I must tell you, a lot of this OEM of product brochures and seminars they conduct, of course, they always have a bias towards their own equipment. Nevertheless, go with an open mind and at least try to learn what is the technology behind them. And maybe the OEMs bring in a lot of new technologies. So try to learn them and then try to see the physics behind them, and then you may be developing your own equipment and so on and so forth. So there's a lot of resources in why only condition monitoring, all subjects. There are a lot of resources, particularly in this pandemic. Professors have made a lot of self-help training videos and courses, and of course, we all of course are there. And my website iitinnovations.com is there as well. Of course, I must thank my sponsors over the last of 25 years. I must have consulted for more than 100 industries in the country. This is quite not the most updated one in the areas of condition monitoring, acoustics, and I must thank them. Of course, no research is complete or no professor will exist without the students. I must thank all my students. This is me sitting here with all my students. The sad part about this picture is all the students will leave, but this old guy only keeps on sitting here. But the students come and go, that's part of life. But they will be good ambassadors of condition monitoring throughout the world. And that is what gives a teacher a sense of satisfaction if the students do the teacher. Okay. Having said that, I'm not done. I'll come to the next slide on MCSA as to the IoT and give you certain. See if I can, yeah. Having said this, I will continue our discussion on the present state of the art on IoT-based fault diagnosis of electric motors. So we will basically, I'm sorry, why is this jumping? Okay. Okay. So I will talk about this spindle motor. Okay. It is provide Internet of Things, IoT-based remote monitoring of electrical motors on real-time basis. I will tell you how it is done. So this technology, which has developed by us, will ensure that the plant personnel can access the motor health report file from the cloud from any location, and it is happening as I speak. Detect faults by using motor current signature analysis. I just had told you the theory a few minutes back. And of course, as goes without saying, avoid catastrophic failure by early fault diagnosis, because it is beneficial for all of us. So as I was telling you, motors are used almost everywhere. 90 to 95% of the prime movers, the remaining being only IC engines, are the prime movers of any plants. Machining, steel, cement, HVAC, mobile equipment, and many more. Everywhere there is a motor. So how can we neglect this? So in a motor, there are electrical faults and there are mechanical faults. Electrical faults, broken rotor bar, stator winding faults, burned coils, etc. Bearing faults because of starved lubrication, because of sparking, arcing, ground loop, air gap eccentricity will come up. And of course, certain torque and overload which can create because of a manufacturing defect. All these faults will get manifested in the motor current being drawn by the motor. So this is how what we have done. The technology which we have done here is, I have a motor here, measure the current, have a data acquisition system, transport to a mini computer wherein it does the analysis, it generates report files, it tells in the Boolean what kind of fault is there and the spectrum of that fault, and it sends it to the cloud. The report is there in the cloud, anybody can access it. Okay, and this is a technology which we have developed at IIT Kharagpur. And then this report can be accessed by on-site, off-site personnel at different locations. So this is the simple current transformer. This cost me in Amazon for about 200 rupees. Okay. This is a National Instrument data acquisition system. Okay. We can monitor 4 channels, 4 motors simultaneously. And this is a mini computer with an Wi-Fi module. Earlier, those of you who are familiar with Arduino and Raspberry Pi may do this, but the problem with Raspberry Pi is the sampling frequency is stable only up to 1000 Hertz. But here, for high fidelity, we require this data to be captured at about 10,000 samples per second. So this is the costly element here. But let me tell you, for the hardware cost for this entire 4 motors, if there are 4 motors, is less than a lakh of rupees, 1 lakh of rupees. Okay, the technology is such. Of course, this, apart from the brain use on the software. Okay. And then I can put the report files into the cloud, which can be accessed anywhere. So I'll just give you an example. This is a typical motor in a Makino spindle machining. Okay, this were we just did a trial study in a plant in Pune. Actually, one of my research scholars is stranded and is in Pune during this lockdown. So over email we could do this, and then he could only go to the plant and install it. I shipped all the hardware to him, and then we developed it, and then okay. This is how. So all we require is just 20 seconds of current data. Okay. The LabVIEW is a commercial software which IIT has licensed, and then we implement it in the software. Okay, this is just an example. I'll show you. This is where we put the current transformer right next to the spindle motor. Okay, and we can monitor the motor. And this is a large machining center, and where the plant was mentioning that they are having a lot of problems with this machine. The motor needed frequent replacement. It was a nuisance to them. They were thinking, their OEM would only tell them the fault once they took the motor out. Then they went to the workshop, they dismantled it, looked into the bearing or the rotor or the stator. But through our technology, you don't have to open it. Measure it on the fly, on your laptop, on your mobile, you will get the condition. Okay, and the current, and then we get to do the analysis, we took the current data. Okay, sampled at very, very high, 10 kilohertz sample. You can see the timestamp. Okay, 1 by 10,000 each one of them. Okay, and we got the current and did the analysis. This is a typical current, and zoomed it, and we looked at the frequency spectrum. And from the spectrum, sorry, go back. Yeah, from the spectrum, this is done in our lab. We can say whether the motor has a broken rotor bar. It can detect all these 5 conditions: broken rotor bar, straight winding fault, eccentricity fault, bearing fault, torque fluctuation. Okay, so this is what we can do. And so this, we have currently doing it for induction motors. I was telling you, with this electric vehicle, a German OEM has approached us to implement it in PMSM motors for electric vehicles. And we will be adding this software to different modules. This is going to help everybody. Okay. So we can have IoT-based system for monitoring any machine through motor current signature analysis. Okay. With this, I will formally end my talk, but then I have kept some time for a Q&A. Okay. Now, I do not see the chat window. Let me see.
So I can read out these questions to you if you like.
Let me see. Let me see. Is the chat window there? No, not there. Q&A.
Okay, I can just copy paste. Maybe just a moment. I'll do it.
Oh, okay. Or you can read. You can read till I figure it out what's going on.
Okay, there are two questions from Mr. Rahul Sinha. Firstly, he's asking what is the best time to do thermography? What are factors that can affect correct measurement?
Acha. Now, with my example, which I showed, if there is a misalignment in the system, because see, eventually the temperature will be uniform throughout with time. So the more time you wait, in a small system, it will be all under equilibrium. But to answer your question, it depends on the applications. Suppose I have a switchboard where there is a loose contact compared to the rest of the conductors which are at the normal temperature. Anytime I do thermal imaging, I will get the same results. But for events which are occurring very fast, like a rate of temperature rise, initially we should do the thermal imaging. What is the second part of the question?
The second part is what are the factors that can affect correct measurement?
Yes, the factor which can affect correct measurements, right? Most important is the surface emissivity. If your surface emissivity value is wrong, your absolute temperature value will be wrong because of the Stephen-Boltzmann law. Okay, because it's a function of that constant because of the epsilon there. Having said that, sometimes even the image which we capture, there could be some reflection. Finally, it is the rays which is coming to the semiconductor pixel. So if your composition of the image is wrong, focusing is wrong, we may get errors. But the most significant error is because of surface emissivity. I hope I have answered your question.
Yes, sir.
Next.
There is another question from him itself. And he's asking, is there any difference between NCSA, ESA, and PDA?
Yeah, they are loosely used. ESA, electrical signature analysis, where they also do the voltage analysis, look into the harmonics present in the voltage. There they also measure the voltage compared to the motor current signature analysis, where we do only current monitoring. ESA is actually a broader, and MCSA is part of ESA. And nowadays, people are also measuring voltage current. Okay. PDA is, is it predictive data analytics or something else? That's altogether different. Okay. Not related to ESA or MCSA. So there are companies doing ESA, they will be doing MCSA, and they will be doing the voltage harmonic contribution also. Yeah, I can read the question.
Yes, sir. So Mr. Sinha is also saying about PDA, it is partial discharge analysis.
That is because of the transformers. Transformers, you can do that because these are all components in the transformers when talking about the dissolved gases, etc. Okay, so ESA is actually the mother. All these could be the subsets of ESA.
Yeah, thank you, sir. So from my side, I would like to ask a small question. Maybe it's not pertaining directly to the area of condition monitoring. Since I'm working in the area of fracture mechanics in composite materials, sometimes we do encounter crack detection problems. So how far
Right.
is this methodology can be applicable over there
Which one, MCSA or in general?
in general, sir?
See, for example, let us take the example of a shaft where there is a crack. Okay.
Yeah.
So look at the crack, the stiffness is going to change.
Yes.
Now, stiffness changes, the system characteristic has changed. So, mechanical impedance, which is nothing but the force by velocity of that system, cracked, uncracked, there will be a significant difference in the mechanical impedance. And there has been a lot of reported literature on finding out cracks in shafts by noticing the difference in the mechanical impedance, be it through finite element methods, be it through experimental method. In fact, my first PhD scholar, Prabhakar, worked on crack detection through mobility measurements.
Okay. Thank you, sir. Thank you very much. And there is one more question. It is from the previous session, I think. There is a request like to explain again some aliasing topics.
Okay. Let us see what we can do. Which topic?
So just mention about aliasing topics.
Yeah, see, signal aliasing, I do not have a pen, paper, or a board here, but let me try to explain to you through words. Suppose I have a sine wave, okay? A nice sine wave. Think of your lab where you drew your graph. You have points very close by. You drew a graph by joining the points which are close by. Now the same graph would you get if I pick the points, not successive, 1 point and the 4th point and the 4th point and the 4th point and so on. That means the time period between the points increased. Okay. So you will no longer get a sine wave, but you will get something, maybe a triangular or a horizontal lines, etc. So that means your original sine wave, which I can capture if I pick up the points very close by, will be lost if I pick up at a larger time interval. Larger time interval means a smaller. Time is inversely proportional to frequency. So larger time means smaller sampling frequency. That is what is aliasing. So if I sample a signal at a frequency less than its maximum frequency, I will get an alias signal. In fact, that is why it is recommended, you must, to prevent aliasing, you must always sample a signal twice the maximum frequency in that signal. That is the Shannon sampling theorem. So we have to prevent aliasing because the computer is after all a fool. Any data you give, it will say that came out of the machine. But your data acquisition should not by itself create errors in the acquired signal. So the computer is going to get misguided. It is aliased into a low frequency signal. So that has to be avoided. And the way it is avoided in commercial hardware is they put a low pass anti-aliasing filter before the A to D process. Okay.
Okay, sir. There are some other questions also. Just a moment. I'll just from Lakshmi R. Chandran. It is a general chat for all panelists. How can we study the fault trend in the motor? How can we model it? Whether we will get any fault trending data, re-access, etc., to study disturbance and model condition. Okay, it's a general message to all, and I think there is one more thing. It is available in the chat. Okay, I think, sir, this is fine, and I would like to thank you very much for your valuable time and for the knowledge you shared. It was really wonderful in uplifting our understanding about this area, and we will be delighted in hearing you in future also, sir. So
Thank you.
It was a pleasure of hosting you, sir. And
Yeah. As organizers, if you could send me the participant list with their email or names, so that we can form a group and they can ask me.
sure, definitely, sir. We will act accordingly. Okay.
Thank you very much. Have a
Have a
good day. Bye.
Bye.